When we look up at the sky, we see all this incredible light stars, galaxies, the whole show. But what if I told you the real drama, the biggest stories, are happening in the dark? Well, today we're going to dive into one of the universe's most fascinating ghost stories. So, here's the cold case that's been bugging astronomers for, well, forever. When we use our telescopes to look way back, to the very beginning of the universe, we see these monsters. Supermassive black holes, millions, even billions of times bigger than our sun. And they're just there, already fully grown. That's a huge problem. It's like finding a giant redwood tree in a garden that was planted just yesterday. It shouldn't be possible. Okay, so who are the usual suspects for making black holes? Well, the first stars, right? Makes sense. But here's the thing. When you actually do the math, the story completely falls apart. See, those first stars, they were powered by nuclear fusion, which means they were incredibly hot. So hot, they were basically blasting away all the nearby gas with their intense radiation. They couldn't eat enough to get big. There was no way they could have packed on enough pounds, fast enough, to become the seeds for those monsters we see. The timeline it's a total bust. So, if fusion wasn't the engine, what was? This is where our cosmic detective story gets really weird, because the answer might be something we already know is out there. It's everywhere. It makes up a full quarter of the universe, but we can't see it, we can't touch it. It's hiding in plain sight. Yup, I'm talking about dark matter. And for our story, we're going to focus on one of the leading suspects for what it is, a particle called a WIMP. That stands for Weakly Interacting Massive Particle. Now, the super important thing to know about WIMPs, at least in many theories, is that they're their own worst enemy. They're their own antimatter. So when two WIMPs happen to bump into each other, poof, they annihilate, releasing a little burst of pure energy. And that little burst of energy, well, that's what leads to this absolutely game-changing idea. What if dark matter isn't just this dead weight holding galaxies together? What if it's not just cosmic scaffolding? What if, just maybe, under the right conditions, it could be a fuel source, a powerful secret engine for a whole new kind of star? Okay, I know what you're thinking. Hang on a second. How can this ghost particle that barely interacts with anything suddenly start a fire? And look, you're right to ask. It sounds kind of impossible, and it's the exact same question scientists have been wrestling with. This question is everywhere on forums and in discussions. It really is the heart of the problem, right? If these things are basically ghosts passing right through you, me, and the entire planet without a trace, how on earth could enough of them ever get together in one place to generate any real heat? And here is the absolute key to the whole thing. The term weakly interacting doesn't mean zero interaction. It just means the chances of it happening are incredibly, incredibly low. But it's not zero. And when the chances aren't zero, you can change the odds with one simple thing: density. Think of it like this, a game of pool. If you've got one ball sitting in the middle of a giant table and you just randomly fire another one across, odds are you're going to miss, right? But what if you pack all the balls into that tight little triangle in the center? Now if you fire a ball in there, a collision isn't just likely, it's pretty much guaranteed. That's the idea with dark matter. Out in the vast emptiness of space, they rarely meet. But you cram them into the super dense core of a baby star, suddenly the interaction rate goes through the roof. All right, so now that we know how it could work, we can finally unmask the prime suspect in our cosmic cold case. We're talking about a completely new type of star, one that could have only existed way back at the dawn of time, inside those incredibly dense clouds where the very first stars were born. So let me introduce you to the dark star. Now, on the outside, it's made of the same stuff as any other star, mostly hydrogen and helium. But its engine? Totally different. There's no nuclear fusion furnace raging at its core. Instead, it's being gently heated from the inside out by the constant, steady annihilation of all those dark matter particles we just packed together. And when you put them side by side with a normal star, you see just how wild these things would be. A regular first star would have been super hot, super bright, and pretty compact. A dark star, on the other hand, it's giant and puffy. We're talking huge, maybe 10 times the size of Earth's orbit. And because its engine is this slow, steady burn of dark matter instead of a violent fusion reaction, its surface is way, way cooler. And that coolness, believe it or not, is its secret weapon. So for one of these ghost stars to actually form, you need a perfect cosmic recipe with 3 main ingredients. First, you need a ton of dark matter packed into the center of a baby star. Second, that star has to be dense enough to actually trap the energy being released by the dark matter annihilation. And third, and this is the big one, the heat from the dark matter has to overpower any other process that's trying to cool the star down. And guess what? Back in the early universe, these conditions were basically perfect. And let's get back to that secret weapon, its cool surface. Because it's not super hot, it's not blasting away all the material around it like a normal star would. It's not blowing away its own dinner. This means it can just sit there, calmly, and keep pulling in more and more gas and more dark matter from the giant cloud it was born in. So it just keeps growing and growing and growing, potentially reaching these absolutely mind-boggling sizes. We're talking up to 10 million times the mass of our sun. And all of a sudden, those giant black holes we found at the dawn of time, they don't seem so impossible anymore, do they? Okay, this is a really cool theory, for sure. But is that all it is? A nice idea? Or could we actually find one of these things? Well, the awesome answer is yes, we can look for them. This isn't just sci-fi, it's a testable hypothesis. And we finally have a tool powerful enough to go ghost hunting. And our ghost hunting machine is, of course, the James Webb Space Telescope. Its incredible infrared vision is basically a time machine, designed specifically to look back to the cosmic dawn, the exact era where these dark stars should have been shining. So what exactly would Webb be looking for? Well, astronomers have this tool called an HR diagram. You can think of it like a family portrait of stars, where they're organized by how bright they are and how hot they are. Normal stars all follow pretty predictable paths on this diagram as they live and die. But a dark star, it would be the weird cousin in the corner doing its own thing. It would get brighter and brighter and brighter, but its temperature would barely change. It would carve out a path on that chart that screams, "I am not a normal star." The technique they use to find things that far away is called the dropout method. It's pretty clever. See, as light from the very early universe travels to us, it has to pass through all this hydrogen gas floating in space. That gas acts like a filter, and it absorbs all the blue light. So when JWST looks at something, it might see it clearly in its red filters, but when it looks in its blue filters, poof, it's gone. It's a dropout. That tells us exactly how far away and therefore how old it is. And here's the kicker. A dark star would be bright enough for Webb to spot it, even from that incredible distance. So let's recap our cosmic cold case. We have the crime, impossibly large black holes. We have a suspect, the dark star. And we have our detective on the case, the James Webb Space Telescope. So how does this all wrap up? And what does it mean for, well, everything? Well, it all comes back to this. Those giant black holes that started our whole mystery, they might just be the skeletons left behind by these dark stars. See, once a dark star finally burns through all its dark matter fuel, it can't support itself anymore. And a star that massive doesn't just fizzle out. It collapses under its own immense gravity, directly into a black hole. But instead of starting small, it leaves behind a seed that's already supermassive. And just like that, the case might be closed. But this whole idea is so much bigger than just solving one mystery. It completely changes how we think about dark matter. I love this quote from physicist Robert Coldwell, who says it's a new approach to thinking about dark matter. It means dark matter might not just be this passive, boring stuff. It could be an active player, a creative force that helped build the very first structures in the universe. So the dark star theory is an absolutely incredible clue in this grand cosmic puzzle. It's a beautiful potential answer to a huge question. But it's also a powerful reminder that something like 85% of all the matter in our universe is still a total mystery to us. It really makes you wonder, doesn't it? As we keep pointing our telescopes into the night, what other ghosts are out there? What other secret engines are hiding in the dark?